So this is the fourth lecture about chapter 1. I hope it's the last one. And chapter 1, probably the longest of the chapter. Other chapter will be 3 lectures each. Okay, so last time I proposed an exercise. Well, an exercise, Euler pentagonal theorem, how it can be an exercise. It's difficult, it's not so easy. But we have some tricks that, the trick is that it's what we call the construction of an involution, changing the parity of the number of rows. Euler theorem means that the coefficient of q power n, the number of partition of n into even number of distinct part, minus number of partition of n into odd number of distinct part. So you see in this big summation, many terms cancel, only a few remains, which one of these seconds is related called pentagonal numbers. So what we want to do in this involution principle is to try to pair the partition 2 by 2. I have a partition, I have to associate the number of row is the parity of the number of row is changing by 1. By the way, did anybody find the solution? Find involution? No? So I will show you. I am not going to give you straight away the involution. I am going to show you the logical thinking to go to the involution in an easy way. Okay, so I have to change the parity of the number of rows. So I am going to delete a row and put all the points of the row in the remaining diagram. So it's a little crazy to try to delete. It can be very long. The easiest way is to delete this row. So you take off this row and you put it here. The most simple idea is to take this row and then to put it on the first row. Now, if you forget what you have done, you cannot go back. How to know that you have put this? How to know? Maybe it was. So it's not going to work to have an involution. Once you have done the suppressing a row and put in the diagram, you must be able to go back to know which Ferrer diagram give you this one. So another idea maybe is to put all the points of the first row in different, not only on the first row, but in like this, in the first and second row. But here, when you put it, partition distinct part means the difference between two parts is at most 1. So I will not be able maybe to put 2 points on the same row. So this is not a good idea again. So the best maybe is to put at most 1 point in each row, like this. But how to recognize, once you have deleted the red, how to recognize? I have no way to go back. So to have a way to go back, in each row for the first, second, third, should be a certain geometric pattern that I can recognize. But a good idea would be to put a geometric pattern like this. To try to put the point in a 45-degree line, in a diagonal. If you have putting the point like this, I have some chance to be able to go back. Because it's a geometric construction. It's the geometry of the point. So like this, for example. Let's take this Ferrer diagram. Here, you are going to take point in the 45-degree diagonal, and why not to take the maximum possible? This is uniquely defined. If you take the maximum possible, longest sequence of point in the 45-degree diagonal on the northeast border of the Ferrer diagram, this is well defined, and I use this red point to put them on the first row. So good, it's bigger. Try to put them in a degree diagonal. So the max the red and the blue. And the involution is to have one movement in one side and one movement on the other side. So we have to make size definition. What is case 1? Go to case 2. So in the case less than the number of elements on the diagonal, then I do this. I take the first row and I can always put, you see in that case, the blue point, I cannot put them on the top. So I am forced only to put the red point like this. But what happens if it is equal to the number of blue points? No problem. You can still do it. But you cannot do the reverse. Because it's going to be a partition with no two equal parts. So I begin to get my case. If the number of elements in the first row is less or equal to the number in the diagonal, this is case 1. Now so I do the involution, and I am in case 2. 2, the number of elements than the number of the diagonal. You see here there's 3 elements. There is 2. 2 in the diagonal. And then you see I can go back. So this is my 2 case. And you cannot have both cases at the same time. You cannot be able to move the red to go on the blue, and cases are completely disjoint. Else you can move the red on the diagonal, which means that the first row is less or equal number on the diagonal, and you do the movement, and then you have case 2. No. Case 2 where this is case 2. Where the number of elements in the diagonal is strictly less than the number of elements on the first row. Now, is involution defined everywhere? No. There is some case I cannot do anything. What are these cases where the involution is not defined? It's this one. When the red point and the blue point intersect, they have a common point, the longest, then I cannot do anything. Try to put the red point, the first row on the diagonal. You cannot do it. Try to put the diagonal. You cannot do. Either way, it's impossible to do anything. And then the second case, where also you cannot do anything. The diagonal intersect with one point, and the number of elements of the first row is one more than the number of elements of the diagonal. You see here, if you do this, I have a partition with 2 equal parts. And if you do this is crazy, you don't have any partition. So this is the 2 cases where the involution is not defined. And the weight, Q power, it depends on the parameter n, and you can check that the weight of such a thing is Q power 3n minus 1 divided by 2. This is the so-called pentagonal numbers, because there are number of cells in pentagon included one in another. And there is another one also, this. And so this gives you a proof of Euler identity. And I don't think if you try to do any other involution that you will find something else. Maybe it's possible, but this is the most simple logical way to try to delete a row, to put it on the Faraday diagram below, and to be able to go back. So this exercise was not so difficult. If you try, if you try to make an involution by trying, going back, then you follow the path, and you should find this involution. This involution, maybe I make a lapsus last time. I was talking of glacier. In fact, this evolution is defined by Franklin in 1881. So you see, killing evolution was a long time ago already. Killing evolution, or sometimes people call this sign reversing involution. It's replaced the inclusion-exclusion principle.
But how did Euler prove it?
Oh, by calculus, he did not do the bijection, but no. That's why calculus, but if you like calculus, go back to Euler, and if you like bijection, go back to Franklin. It's but as this classes is in phases and bijection, I will not spend time to show the Euler proof. So exercise, the spirit of sign reversing involution, give a proof that the generating function for heaps of dimers, we have defined heaps of dimers on the segment. There was an exercise with semi-pyramid. There was a logarithmic example with pointed objects. So show that the generating function for heaps of dimers is just the inverse of the Fibonacci polynomial. Here is a heaps of dimers. Here is the Fibonacci polynomial. So you have to prove the generating function of this is this kind of heaps, where there is a -1, a Fibonacci polynomial, a generating function for such trivial heaps of dimers at -1. So to use the philosophy of sign reversing involution, the same as the proposition, the sum of the weight of the path in numerator divided by numerator. So what you have to do is to multiply this Fibonacci here by the weight generating function of heaps, and you have to, everybody must cancel except something which will be the empty, everybody empty will give you 1. So take such configuration of dimers, any configuration of dimers on the segment 0K, take any heaps, and then you have to associate to such pair another pair where the sign will change. So to change the sign, everything is plus, so you have to take one dimer here, delete a dimer, and put it on the heaps. Or maybe take a dimer from the heap and putting back here. So you have to, this is more easier than the Euler pentagonal theorem, but you should be able to do that. To have an involution which associates to such pair, another pair, where there is the parity of number of dimers is going to change. So the simplest way is to delete one dimer, to put it somewhere in the heaps, and conversely, to be able to go back. So with all what I have done before, you should be able to do that. If not, come to my office and I will show you, or later in the class, I will show the solution. So more things about rational generating function. So proposition, a characterization of rational generating function. Each time there is a theorem with calculus, I will skip the proof. You can find the proof in classical book like Stanley Enumerative Combinatorics. This class is on phases of non-bijection, and I have no time to do also a lot of calculus, so you can find it in the classical literature. So the three following conditions are equivalent. I take the ring to be the complex number. You take some coefficient beta 1, beta k in complex number, and for a sequence an of complex number, the three following conditions are equivalent. So first, the generating function of this an is a rational fraction where d is this polynomial of degree strictly less than k, with this is the coefficient of the polynomial. If the degree is bigger than k, then you just have to, you can simplify, put a polynomial plus something where the degree is less than k. Second condition, for every n, there exists a linear recurrence relation with constant coefficient. The coefficient is precisely the coefficient of the denominator g. And condition 3, if you take the 0 of the denominator, the pole of the rational fraction, so maybe there is some multiple roots of the denominator, which degree ki. So the an can be put as a sum of power n of this 0 of the denominator, multiplied maybe by some polynomial, where pi are polynomial of degree less than ki, the multiplicity of the roots.
Condition 2, there's only d is there, there's nothing about n.
N is here, it's a... n, no, there is nothing.
Oh,
NaN, for NaN, it will be the same recurrence relation, but of course, the initial, if you change the initial condition,
it's the initial condition.
this initial condition will give you the explicit So if you want to really to compute the coefficient here, you are sure that it's going to be the sum of the power n of all the roots, but if you want to find really the initial, the polynomial here, you have to, in function of the initial condition. For example, if all the roots are distinct, then you have, this will be constant, some constant, so you have, the constant will depend of the initial condition, and the more the recurrence relation is long, the more you need of initial conditions, the first term, second, third, fourth, etc. So I will not prove this, but you can find in a classical literature that the three conditions are equivalent, but it's good to know that when you have a rational fraction, you can express explicitly the term of an in terms of a sum of power of the roots of the denominator. Or that you have a equivalently linear recurrence relation with constant term. We have seen that if the recurrence relation with polynomial term, then this is the so-called D-finite generating function. For example, the Fibonacci polynomial, then there is two roots of degree each of multiplicity 1, and this is explicit expression. You can get a classical expression for Fibonacci. When you take the transition in the related to physics, when you take the transition matrix method, you have the determinant, or the sum of the weight we have seen, we have the determinant of this. So the AN can be an expression in the inverse of the zero of the polynomial. Be careful, it's not the zero, it's the lambda I are the inverse of the zero of the denominator. So in case you are working with this transition matrix methodology, the sum of the weight of all the paths in a certain finite set, then AN can be expressed at the inverse of the zero. That is exactly the eigenvalue of the matrix. So physicists, when they have a transition matrix, immediately they want to compute the eigenvalue. The biggest eigenvalue will be the main term of in the expression of AN. Well, I try to relate. There is different language in combinatorics, in physics, in computer science. So I try to relate the three philosophies. For example, the zero of the Fibonacci polynomial. We have seen last time that every matching polynomial of a graph has real zero, especially the Fibonacci, Lucas polynomial, Hermite, Laguerre, etc. have a real zero. In the case of Fibonacci, then you just apply the relation between Fibonacci polynomial and Chebyshev polynomial UN second kind, and you get an explicit expression for the zero of the. You just apply this, apply the zero of this, and then you get, by trigonometry, the zero Fn. So sometimes you can see very often in literature something like this. This means you are working with something related to Fibonacci or Fibonacci polynomial. For example, the bounded Dick path explicit expression will involve the zero of this trigonometric of the Chebyshev or related Fibonacci. Especially the exercise of inverse of generating function of hips of diamonds will explicit expression will involve this cosine of this explicit expression. Again, for the other Chebyshev with Lucas polynomial, then you can easily find the zero of this, the zero of cos and theta by trigonometry. You get this, and related to Lucas, with the relation with Lucas and Chebyshev, you get the zero of the Lucas polynomial. So another calculus famous formula, the Lagrange inversion formula. So we will use it sometimes. It's a very classical way to compute the coefficient of generating function, especially in the case it's algebraic generating function. So here is the Lagrange inversion formula. I take a field of characteristic 0. So I take a power series, and I am trying to find the reciprocal of the power series. Means that if you substitute this power series in f of y must be equal to t. It's reciprocal for the composition of formal power series. So to be able that this reciprocal exists, you must have f of 0 equals 0 and f prime of 0 different of 0. So the first term of minimal degree of f must be t, must be begin by t, or a constant times t. So then I can, to inverse the reciprocal of f, if I write f as t divided by phi of t. I can always equivalently write there exists a phi such that f of t is t over phi de t. This will be more convenient. Phi of 0 will be different of 0. So then y, what I am looking for, is a unique solution of this equation. Y is equal to t phi of y, with the constant term y of 0 equals 0. Okay, so to solve the reciprocal of a generating function is equivalent to solve this kind of equation. You give me a phi with a constant term non-zero, and I want to find y such that y equals t phi of y. And Lagrange inversion formula give you an explicit expression for the solution of this equation. Even a little more, I can involve another power series g. Instead of computing the coefficient of y, I am going to compute the coefficient of g of y. So let's g to be a formal power series in variable t in the ring of coefficient k. Then I claim the coefficient of t power n in g of y is this. So the notation, this means I am taking the coefficient of t power n in g of y. And Lagrange inversion formula tell you that this coefficient is 1 over n divided by the coefficient of t power n minus 1 in g prime of t multiplied by phi of t power n.
Sorry, I don't understand. What happened to... So you're trying to find the inverse of t by phi t. G is the inverse of...
No, g is any power series.
Okay.
I make something more general. You see, at the beginning, I was trying to find the reciprocal of f. I transform it in an equivalent problem to find the solution of this equation, y equals t phi of y. So I have the Lagrange inversion formula, give you a solution which would be if g equal identity, then if g is identity, then the coefficient of t power n in y is equal to the coefficient on 1 over n, t power n, the coefficient of this would be 1. So it will be the coefficient of t power n in phi of t power n. If g is identity, then that was my initial problem. But I am something, it's more useful to have something more general. When you have a NAG,
Sorry, what is the g you put?
no, anything, G, anything.
How do you get back to a special case?
Special case, G equal, G of y equal y. So G of t is t.
Oh,
If G is equal to t, then G of y will be y. So this will be y only.
same y as the...
Yes, G of t equal t, so this will be y, and this will be 1. So the coefficient of t power n in y is equal to 1 over n, the coefficient of t power n minus 1 in phi of t power n. So this would be the solution of the initial problem. And more general, it will be useful to have this more general Lagrangian formula with any formal power series G, and you get this formula. I will use it, I will show you an example with planar maps to use this Lagrangian formula. So there is an analytic proof with residue of meromorph function. I will skip this proof because in the next chapter, maybe it will be in chapter 2. I'm going to interchange 2 and 3. Now I change my mind. So I will give you a commutative proof of Lagrange inversion formula. It's classical proof due to Rane in the 60s with a cyclic principle. Cyclic lemma principle, which we can apply in a different situation. So wait for the next chapter to get, there's a nice direct commutative proof of this formula. Example with Catalan. So the Catalan generating function satisfies this algebraic equation. I want to compute from the algebraic equation the value of the Catalan number, the Cn. So I want to reduce my problem to this kind of equation. So if I just change y in z equal 1 plus y, because Catalan starts with 1, I need a function starting with a monomial t. So if I make this change a variable, then I have this, the z satisfies this functional equation. Z equal t phi of z, where phi of t equal 1 plus t to the square. It's easy calculus to change this equation into this equation. And then you apply Lagrange inversion formula with the function g reduced to g of t equal t. And then the coefficient 1 of Cn will be 1 over n, t power n minus 1. The coefficient in 1 plus t power 2n, which is exactly easily this, and this is equivalent to the Catalan number. So you can get from the algebraic equation, by a change of a variable, you go back to this functional equation, and then you apply Lagrange inversion formula in the case of g equal g of y equal y. There is no g, and then you get the Catalan number. So the next section is, from the beginning we have algebricity for dict path, for binary tree, different kind of thing. Algebricity is obvious because you have obviously a decomposition of the commental object into smaller commental object, and this decomposition reflects an algebraic equation, give you an algebraic equation. Decomposing a binary tree into a pair of two binary trees give you immediately the algebraic equation for Catalan number. But there is some other very classical commental object where the fact that it's algebraic comes from a decomposition of the object in smaller object, but it's not at all obvious to find this decomposition. And then that's the interest of bijection, bijective combinatorics, is to do bijection to be able to find the decomposition, and from this to get algebraic equation. So one of the most beautiful examples is planar maps. So I recall that the planar map is a set of points with some edges. So it's like a planar graph, and you embed the graph in the plane. So maybe there is multiple edges, maybe there is loops, and in fact your planar maps is not on the plane, but it's on the Riemann sphere. So you can make deformation of your picture. For example, these edges, imagine in the Riemann sphere. So you can take these edges and put it and go along the sphere like this, and then you can put it here. So the deformation is on the sphere, not on the plane. And Tutt in the 60s made a series of papers for many, many years about counting planar maps. He wanted to do that, to count planar maps with four colorable, and then if you find the two geometric functions are the same, you get a proof of the four-color X conjecture. But to count planar maps is not easy. It's much better to count rooted planar maps. Rooted planar maps means one of the edges is pointed. You take one of the edges, and you take an orientation on the edges. And then you can really have nice formula for rooted planar maps. And Tutt shows that if you take an, the number of rooted planar maps counted by number of edges, not the number of vertices, number of edges, then this geometric function is solution of an algebraic system of equation. The number of planar maps is going to be equal to this, where z equal to this. So if you have this system of equation, give you exactly the geometric function for planar maps. So by a few calculus, to be able to apply, to have better formula, this equation for the z can be rewritten like this. If you multiply by the denominator. So now we are in a good hand, because if there was not the 3, then this looks like the Catalan numbers. So if I write z equal t multiplied by h, to have a power series beginning with 1, then I get, from this equation, I get this equation. Good. This equation, the coefficient of this equation, obviously, if there was no 3, there would be the Catalan number, but here there is a 3, means that in the recursion you take a binary tree, and there is each time you take a vertex, there is three possibilities, which means it's 3 power n Catalan numbers. It's a binary tree where each vertex has 3 possible colors. So it's very interesting. The binary tree are behind the planar maps. Planar maps is a 3-color binary tree with some enrichment. You have to put more edges and to choose maybe not all the 3-color binary tree. So let's look the y. So if you go back to the y now, and you write the y in terms of h. So y is 1 minus 4, so z is th, and 1 over this, so this is h2. Now you can put the h in factor, you rewrite it like this, and considering this equation, easily you find this. So the morality is that you are taking 3-color binary tree, and planar maps are exactly 3-color binary tree minus something which is in bijection with the triple of 3-color binary tree. So there must be some deep explanation of this in terms of planar maps. So here is a better system of equation for counting planar maps. And the first bijective proof of this, by taking this kind of 3-color binary tree and subtracting this, have been done by Corey and Vauquelin in 70. So they give a bijection. They give a bijection with a coding of the planar maps as the difference of what is called in theoretical computer science the difference of two words of algebraic language. And we will see at the end of this class what is this philosophy, which is called sometimes Sutzenberger methodology, to encode a commutative object by some word, and this word belongs to what we call in computer science algebraic language, or context-free language, because compilators, they work with grammar, and it's very related to computer science. So I like to make some connection with different fields, because people, they speak the same thing in different vocabulary, in physics, in combinatorics, and in computer science. Sometimes it's exactly the same thing with 3 different philosophy. Now if I want to have the number of planar maps, I'm going to apply Lagrange inversion formula on this system, on the first system of equation, which I can write y is g of z. Yes. So y is g of z, where g of t equal this, and I can write z equal t phi of z, where phi of t equals this. So now I have exactly put my system of equation in terms of to apply the general Lagrange inversion formula. You see the interest to have a g now here. I want to compute the coefficient of t power n in y. So in this, where g of z, where I know g, and z solution of this functional equation with the phi in the form of the Lagrange inversion formula. So apply the formula, you get this. So believe me, you are not going to read you apply the formula, t power n, the derivative of this. So derivative, you have to compute, find the coefficient of this. So this minus this, and you do, and at the end, you find the Catalan number, 2 times 3 power n over n plus 2 Catalan number. So again, very nice formula. Catalan 3 power n divided by n plus 2. How is it possible to have planar number of planar maps? It's very, very beautiful. It's a binary tree, again 3 power n divided by n plus 2, and twice this. So we are trying to find explanation. So this will be different from the explanation of Corey-Vauquelin, which was the difference of two algebraic lengths. Now it's a direct formula, which is much simpler, even most elegant. So Cn is the number of binary trees, the Catalan number. The number of binary trees is n internal vertices and n plus 1 external vertices. So this is the idea of Scheffer, which I will completely explain in the next chapter about the Catalan garden, bijection related to Catalan. So, but I have to make n plus 2. So n plus 2, and there is n plus 1 external vertex, but n plus 2, I have n plus 2 if I add a new vertex. This is the root of the binary tree. If you add a new vertex, now I have n plus 2, but I have to divide by n plus 2, so intuitively dividing means you forget it was a root vertex, and you take the tree up to cyclic, you are going to look the tree cyclically. But all this I will just give you a rough idea. I will explain this in the next chapter. So n plus 2 is this, and then what is 3 power n? So Scheffer introduced the blossoming tree. In each vertex, there is a flower. There is 3 possibilities to put your flower or a bud, a bourgeon, blossoming tree in the spring. So this is 3 power n Catalan number. Number of external edges is n plus 2. And then what he do, he make a certain process to associate, to put the edges of the planar maps, starting from the flower of the blossoming tree. And he gets some tree are not balanced, are bad tree, and some tree are well balanced, which explains the difference between the two of Corey-Vauquelin, the two generating functions. So you have a bijection between what he call well-balanced tree and planar maps. See, the idea is to take a binary tree, extend it to put blossoming, and then putting a lot of edges in a nice way. So it's very subtle. You have to turn around the tree cyclically, and then you get a planar map, and this is the bijection. So for any planar maps, router planar maps, there is an underlying tree and going back in the bijection. And then all this was very excited with physicists. They do some others, there is some mobile, there is also bijection, other kind of trees. So there is many work have been done, especially in physics, because this is related to quantum gravity. They want to have information on a random planar maps. So the universe is supposed to be a random planar maps, and you have to find geodesic in this, some other parameter, and some new other bijection. There is many bijection appear, which fit very well to the problem of physicists. And this would have been impossible to solve some physics problem without this fancy, with sophisticated bijection. So you see, then there is the first part is bijective, second part is physics and probability and calculus, and combining the two, you have some really very nice new result. So we'll completely give the proof of this construction in the chapter about Catalan bijection, and I decided to make the next chapter. So another nice example of something algebraic, which is not obvious to see that it is algebraic. This is a so-called directed animal. This problem comes from physics again, from the kind directed percolation or some other problem in physics. And the problem is easy to state. So you have the square lattice. A directed animal, you put a set of points in green. This is the origin. The red point is the point 0, 0. And a directed animal is a set of points on the square lattice such that every point of the animal can be reached from the source point, from the origin, by a directed path, means the path which is completely included in the animal. And the elementary steps of the path are two kinds. You can go from one point to another point by the north, elementary step, or you can go east, elementary step. So this means directed, the animal, if you put the point one by one, it tends to grow to the northeast direction. So this is related to directed percolation. It's like you have some fruit trees and some infection disease are spreading, but there is some wind. The infection is spreading by the northeast west, and the complete problem solution of the directed percolation is you have to count such things, equivalent to count such things, by the number of points plus what is called the directed perimeter. but I will not insist. I will go back to the more simple problem. How many such animals having endpoints? You have to count. This is the first problem given by physicists. It was related to other problems like a gas, hard gas model, etc. It's equivalent to count the number of such things having a given number of points. So you see, when this point, when I say directed, you can find a path. Maybe you can find several paths. For example, a Ferrer diagram is a directed animal, very compact directed animal. The directed animal can be also very, with a lot of hole, can be very thin, very. So you have many different sorts of directed animal. So if you find the directing function for the number of directed animals with endpoints, it satisfies the following system of algebraic equation. It's very simple. So it's not obvious from the definition of directed animal that you can really find this system of equation. And the surprise is that this system of equation is exactly the system satisfying by this path. The beginning of a Motzkin path. So you take such path, you see, you go, it's path with three kinds of steps. You start at the origin 0, 0. You always stay above the 0 level. And you can, three kinds of steps. You can go northeast, you can go southeast, or you can go east. And such path, you finish any level. So we call this the beginning. If you finish at the 0 level, you have what is called a Motzkin path, because it's counted by the so-called Motzkin number. It's kind of extension of Catalan, where you have a lower level in the path. But prefix or beginning, it's a beginning of a Motzkin path. You finish at any level. So exercise shows that the beginning of Motzkin path satisfies this algebraic equation. So this is an easy exercise. With everything we have done with Dick path, with the algebraic equation of Dick path, you can easily show that this system of equation is satisfied by this kind of path. And the y is the beginning of Motzkin path, and the z is exactly the generating function for this kind of path. But then how is it possible to show that this system of equation is the same as the system of equation satisfied by directed animal? So this is I will not give you the proof, but it's just to give you some example of nice coordinate object with a hard decomposition. On the Motzkin path, it's immediately, it's like the Dick path, but how you can find, you have to find a bijection between such animal and the beginning of a Motzkin path.
What is Z?
Hmm?
What is Z represented?
Z, here, it's a kind of analog of the semi-pyramids on triangular lattice instead of square lattice. So it's a kind of animal. This kind of animal where if you take this diagonal here, it's all the animal is above this diagonal. So this would be the Z. It's a semi-animal. So now it's this kind of things are, again, we will see it's algebraic language, and there is a methodology to find a random word. Random means I am going to take a word. It's encoded a word in 3 letters. Now these paths are encoded this word in 3 letters. They satisfy some algebraic equation, and there is some standard technique to have an efficient algorithm to find random words of length n. Random means that you take all the words of length n, and each word appears with the same probability. So if you have a nice bijection between this directed animal and this word, which are a one-dimensional word, in fact, this Motzkin path is a path going on the vertical line. You go up, down, each time you go up or down, up the next level, down this level, and maybe you stay at the same level. So in fact, it's not a two-dimensional path, it's a one-dimensional path. So I have transformed a two-dimensional directed animal into a one-dimensional picture, which is much more easier. So you can find random word of length n. There is some efficient algorithm. So this is another part of combinatorics, random. There's a whole new field developing to find random So, if you look at, take a random word of length n, you can make n equal 100,000. You can go very fast, very big, because the algorithm is very efficient, and you can find picture of random animal. So before I show you a random animal, try to imagine in your mind what is a random animal. Ferrer diagram, don't forget Ferrer diagram is an animal. If you have an animal, a set of points, only a long line, it's an animal also. So what is a random animal? You can give this to students in computer science. They will write the program. As soon as you see the picture, you can say that if the algorithm is right or not, or here is a random animal. Or maybe 10,000 points, or here is another one. So it's a pride, it's a very, very thin.
So these are seen in disease spreading.
Yes, also. Next time I will make a window on the disease and Strahler number. But you see, there are very few loops. It's very, very few. An anecdote about this directed animal. This problem was posed by physicists, 3 physicists in Paris. So they are not so. They were young physicists at that time in 82, 83, and they were working to find the number of directed animal. So they cannot find the solution. They asked to different mathematicians, and then I received a letter. And then what they have is a conjecture. They have the way they solve this problem. So no, they did not solve. They make a conjecture. The way they do it is the following: you put your animal on the bounded strip. You fix the beginning, the source point. There is 3 source points. You put them on a finite strip, and then you cut it here. See? So you have a transition matrix methodology. Each time you cut your animal, there is 2 power n possible state, and you go from one state to another one. There is a transition. You cannot do, because of the directed, you cannot go in, there is another state. The weight of the transition is the number of points. So you have applied the methodology we have explained in this class, transition matrix, finite transition matrix, and then they conjecture this as a total number of directed animal with a given source point on the bounded strip. Even it was more, because the bounded strip, you see this is not a directed animal, but the bounded strip in fact is on a cylinder. They take animal on a cylinder, they make cylinder bigger, bigger, and bigger, and they conjecture this formula, and if you go, the size of the cylinder go to infinity, then you will, this go to 3. And then you recognize now the 0 of the Chebyshev I gave you before. So the anecdote is that they discovered this by pure experiment. There was a coincidence. There was 2 people working on 2 different computers, close together. One of the man was trying, he gets the real value of this with the decimal of these numbers. And the other physicist was working with called Beraha number. Is a 0 of some graph, which are 2 plus 2 cosinus this. And this 0, it's some chromatic numbers which go to 4, which would prove that the Fokker conjecture is not true at the infinite. And if it's a 0 of a chromatic, we stand to 4. And so this is called Beraha number. It's a 2 plus 2 cosinus. They look, the 2 pages close together. It was exactly the same decimal with a shift by 1. So they conjecture that it was explicit. From the real number, they conjecture it was this, and they conjecture by usual technique. They conjecture this, and then I received the letter, and in fact, all this can be proved very easily with heaps of diamonds on the cylinder, everything. And so it was funny to find, by pure coincidence, to find the explicit value of a root just by looking at the decimal and looking what it was doing on the mind close. This is the 0 they have discovered. So complement, maybe I cannot resist to give you this this convex polyomino. We have seen polyomino. It's this kind of thing, connected set of cells, so that if I delete the border, it's still connected. If you replace each cell by a point, this will be an animal, and directed animal is a special case. And there is 2 problems on polyomino. What is the number of polyomino with a given area? Given number of cells. So for the directed animal problem, it was number of points. It was the area problem. or maybe the number of polyomino by perimeter. And we will say a polyomino is convex for the direction L. It's vertically convex if the intersection of the polyomino with any vertical line is a convex segment. Exercise, a little more difficult than there was an exercise with Fibonacci number. So the number of directed and vertically convex polyomino. See, so you have this kind of thing. It's directed and vertically convex. In fact, it's made of column. You take a sequence of column, but each time the column has to be shifted upwards. So it's not so complicated structure. And surprise, the number of such things is Fibonacci numbers. Example, if you don't believe me, 2, 5, 13. Fibonacci numbers of even index. So to do this exercise is you should apply the methodology of coding this with encoding a bijection, the transition matrix, with some path in a finite graph, which will give you the Fibonacci numbers. If you try, so you take a graph with 1 point, so you follow the column, so you are going to the first point, you make a loop, so I put some point, some point, some point, some point, and then I have to start a new column, but I don't know where, so to start from here, so you should do, when you read the first column, sometimes you should make a mark that, okay, I will start the second column from this step. And then you continue, and then you decide to stop. Okay, so you know where you have to put the first cell here. And then you continue, and then you change your state, and you say, okay, I will put the next column starting from this. So this is the idea, you see. The idea is to, what we call in computer science, finite automata. Or transition matrix, or path on a finite graph. I will show you the finite automata before the end of this lecture. So this is the idea, finite automata, transition matrix on a finite, path on a finite graph. All this is same philosophy, same methodology, which are in different language. Now what about if you do vertically convex plus horizontally convex? So what's the so-called convex polyomino? So then the generating function for convex polyomino by perimeter is an algebraic generating function with an explicit expression and a very nice formula you can deduce from the expression of the algebraic equation. And this was done a long time ago we done this with coding a convex polyomino by a bijection with some word of an algebraic language. This is the so-called Schutzenberger methodology, which I'm going to explain briefly. This will be an incursion in computer science with automata and algebraic language. And then again, because we have a bijection between such convex polyomino and words of algebraic language, then there is some standard techniques to find a random word of the algebraic language which give you this picture. This is a random convex polyomino with a given perimeter. The perimeter is fixed, and this is a random. The color means something. The color, because algebraic language, there is algebraic grammar, and each color means you are applying one of the grammar rule, let's say. Now you can ask, the more difficult, convex polyomino enumerated by area, the Q analog. So we have some formula, and there is some algorithm to find a random convex polyomino with a given area. And here is a picture of a random convex polyomino with a given area. Here is a picture. It looks like a directed animal, very thin. But random convex polyomino, in fact, there are two kinds. There is this one and there is this one. They are split in two different classes. Else you will find this, with probability 1/2, else you will find this. So this is another part of science, the application of bijection to have a very efficient algorithm to give some random objects which are interest by itself to have a picture of or to analysis of random. So let's do a little incursion in computer science to have the flavor of this language, algebraic language, and a flavor of theoretical computer science about, this is related to rational and algebraic generating function, what we call Schutzenberger methodology. It's a coding, a one-to-one correspondence between the object, like a polyomino, the etude animal, and words of algebraic language. So first, what is an algebraic language? Usually, in English, it's called context-free language, and in French, we say langage algébrique. I think it's better to say algebraic language. It's a rational algebraic definite. So it's a word generated by an algebraic grammar. I will not define in general, but I will give you an example of the DIC words. So a grammar is this. You start with, you have some capital letters, and you have a terminal alphabet. So here you have two letters, D and T. X and X bar is a terminal alphabet. The word will be at the end in X and X bar. And you have what is called a grammar. It's a rewriting rule. You can replace D. Each time you can replace D by T times D. And you can replace T by X, D, X bar. X is a letter. X and X bar are two letters. I am working on the alphabet X and X bar.
Oh, okay, so alphabet is X and X
The alphabet or final alphabet, the word will be on X and X bar, the word of the algebraic language, and capital T, capital D are extra letters that I need during the process to generate the word, but at the end, they will be eliminated. You are going to see an example immediately.
Do we think of capital T and capital T as words?
Oh, during the process, it will be word in the mixture of these letters and the small letters. At the end, there will be no more capital. This is the empty, epsilon is the empty word. Let's give an example like this, you see. This is an example how it works. So you start from initial letter, like the C. The roots of the process is you start from D. Then you replace, here, you replace D by this or this. So let's replace by the first T, D. So you have the choice now. There is two different choices to replace T and D by one of the grammar rule, but let's do this one. T becomes X, D, X bar. And then you continue by each time you replace one of the capital letters, D or T, you replace it by this or this.
You're saying DIC paths have this.
And then at the end, the language generated by the grammar is all the words in the terminal alphabet, means all the words in X and X bar, which you can obtain by this rewriting rule. And what we get here is a DIC, the DIC word, the DIC path. But you see, during the process, there is many different choices. Here I make the two choices in parallel because they are really disjoint. Or maybe you can make the leftmost choice each time, but...
Sorry,
yes?
Can you just go back? So in the third step, you have kept D as B in the final.
Here?
No, from
Only
2
one
to
change
3.
every step.
Oh, there is only one change every step.
Yeah, if every step you have one change. But instead of putting this change and this change, I do the two in parallel. If there is no to accelerate the process. Only if you have two different letters. But usually, no, it's one step by one step. You replace one of the capital letters by one of the grammar rule, and then you continue until at the end you stop when there is no more D on T. There is only X and X bar.
So how do you decide which one to choose?
Oh, any choice. Start from when you have a mixture of D, T, and X bar. Take at each time any choice you want. I define the word, the language generated by the grammar is all the word you can obtain by this substitution one by one according to the grammar. All the word you can obtain, which at the end are only in X and X bar.
So you're allowed to introduce new letters, but in the end
Yes.
you have to remove them.
There is some new letters during the process, but at the end must be only what is called the terminal alphabet. At the end, you have only the small letters appearing.
So those other things are not in the language.
No, it is not in the language. They are waiting for somebody. And what you get is exactly, see, in this is a possible grammar to generate Dick words, which Dick words are nothing but Dick pass. So I remind you a Dick pass. This is a Dick pass. It is encoded by a Dick word, x, x, x bar, etc. And a Dick words can be defined, of course, a Dick word is all the word in 2 letters. This is a free monoid generated by 2 letters, such that satisfies the 2 conditions. There is the same number of x and x bar in the word, which means that when you start the path, it's going to go back to the 0 level. Second condition, for every factorization, so every left factor of the Dick path, the number of occurrence of x in U is bigger or equal to the number of occurrence of x bar, which means for at each time, the path is above the x-axis. And at the end, it goes back to x-axis with condition 1.
So T is the first time it's coming back to the path. In that previous generating grammar.
Yes, it's...
T as the
if you go always...
coming back to the horizontal line for the first time.
Yes, yes. If you...
Encoded by T.
But if you write... If you replace T by this, so you get D equal x, d x bar d, and correct, because this is going to be, T is going to be the primitive.
T is the first time it's coming
But
back.
T is not there in the
No, but the meaning, T, you see, D is generating Dick path, Dick words. T is generating what is called primitive Dick path. Primitive Dick path means that you start at 0. You always are above the 1 level, but if you write if you write D equal x, d x bar d, then you get exactly the decomposition. X d x bar d is exactly the first time you touch x-axis. You have a decomposition. Here a Dick path. This is a primitive Dick path. This is another Dick path. This is exactly the.
I mean, once you know the meaning of D and T,
Mhm.
it's easy to see that.
Yeah,
this is the
yes, it's correct.
free grammar generating.
Yes, correct. This is D give x. This is T. The first. If you write the first rule grammar, D equal T multiplied by D. So this is T, the first rewriting rule. T is x multiplied by D multiplied by x bar, and this is again D.
But it's far from unique, so you can't really generate random Dick paths.
No, when you write, if you write D equal, if you take these 2 substitutions consecutively, so you have D is replaced by x, D, x bar, D. So this decomposition is unique. Because you have the first step you go, this is the first factor, which when first time you go back to the 0 level. And then what remains is NA Dick path. You have the unique decomposition.
So that's a canonical,
So it's a kind of a...
canonical form, right? Because
Mhm.
it's not the unique way to write.
So there is no canonical way to do that, but if you do always to the left, then there is a unique way. In fact, you can make this as a tree. All the possible rewriting, you can write this as a tree. What I have done, and then this is called the derivation tree. So when you have a word, this is possible. To get this word, you have an underlying tree behind it. You can get it by doing all this substitution, but you can make the substitution in different order, and you get the same word. Any word will have a derivation tree related to the grammar. A possible rewriting, which give you the same word.
So the
Well-
automaton just has those those 2 states, T and
Here there is two.
2 states, T and D. No.
In general, algebraic language, you can have many non-terminal letters, many letters, but in fact, there's only three grammar rules with only 2 extra letters, but you can have any numbers of letters. And we will say a grammar is ambiguous if there is 2 different derivation trees giving the same word. For example, this one giving the Dick words. This is another grammar giving the Dick word, but it's ambiguous grammar. Because if you do this substitution many times, you are getting intuitively a Dick path as a product of Dick path, and then this substitution you can make anywhere. When I have the previous grammar here, the substitution is always the first one, which gives you the decomposition of the Dick path the first time you reach this zero axis. So in this example, you have the same language, but some grammar are what is called non-ambiguous. This one is non-ambiguous. You can get each word will have a unique derivation tree, and this grammar, giving the same language, can be ambiguous. I define ambiguous grammar to state the fundamental theorem relating all this with algebraic power theory. So the Chomsky-Schutzenberger theorem tells you that if you take L, an algebraic language, so you can imagine what is a general algebraic grammar with many rewriting rules, and suppose there is a non-ambiguous grammar for defining the language, then the generating function for the number of words, all the words of the language of less n, will be an algebraic power theory in the ring of power theory with the coefficient in the Q, in Q, the rational number. So it is a way to produce algebraic generating function. For example, the convex polynomial, the directed animal, all these examples of planar maps, they can be encoded by in one-to-one correspondence with some algebraic language generated by an algebraic grammar, which is non-ambiguous. If it's ambiguous, then it doesn't work. So we have seen the Dick language. It's at the same time you have an ambiguous grammar and non-ambiguous. But there is some language which you cannot find any non-ambiguous grammar. All the grammar you can find, all will be ambiguous.
What is NB?
What is?
NB in the parentheses.
Number of words.
NB, numbers, oh sorry. Number of words.
Is non-ambiguity related to canonical forms for the sequence of moves in which you are constructing? Is it the same thing?
It's related, yes, to. But some language has what we call inherent ambiguity. You cannot find any grammar, they are algebraic, but inherent ambiguity. I mean, there is no grammar which is non-ambiguous. And maybe genetic function of words will not be algebraic.
But if it is ambiguous, is that still a nice class or is it completely bad?
No, it's bad. No, it's inherent ambiguity means there is no grammar which are non-ambiguous.
But is it still like can every language be generated by such a grammar, an ambiguous grammar?
Maybe not ambiguous.
No, to apply the theorem here, you must find a non-ambiguous grammar.
But
And
you
we have
could have a language where there is not even an ambiguous grammar, right?
It exists. It's called inherent ambiguity, means every grammar you will find to generate the language will be ambiguous. Because at the same time, we have seen the example of Dick language. It can be at the same time a grammar non-ambiguous, but Dick words. But as soon as you find one grammar non-ambiguous, then you can apply the theorem. You see this theorem, this is the flavor I have introduced in chapter 0, in chapter 1, the generating function, formal power theory, non-commutative variable. If I take one into double bar, it's a characteristic power theory of the language. The formal sum of all the words in the algebra of non-commutative variable with coefficient in k. And this decomposition of Dick path, the first time you reach x-axis of this rewriting can be written like this. You see, it's a. So this is the philosophy, I write this like this, to have the philosophy of taking coding with algebraic words. In fact, it's not so powerful as all the bijection, for example, Schaeffer bijection, all this, but we are intermediate level between the level of bijection and on object and the level of power theory. Because when you have the grammar, everything, the decomposition, you reflect, if you write the grammar in terms of non-commutative power theory, then you can more or less see the decomposition. You are close to the generating function. As soon as you commute the variable. So it's a philosophy which is between the world of Coulter-Levy, when you can take the sum, the product, substitute, you can really word in the term of Coulter-Levy, in the world of generating function. Intermediate level is this language, non-commutative power theory, etc. So, for example, this the word in X, A and X bar, the left factor of Motzkin path, which are in bijection with directed animal, are some algebraic language. There is algebraic equation, there is... Now I finish with this methodology of Susan-Berger with a particular case. Instead of algebraic language, you have a rational language, a smaller class, which corresponds to rational generating function. So a rational language is a word accepted by a finite automaton. Finite automaton is this. You have some states. You think of the graph or the transition matrix method. You have an alphabet. There is some transition function, initial state, final state. Transition function is you are in a certain state. You are reading the letters, and then you go to another state. And this is the analog of transition matrix methodology, and how it works. It works, sorry, transparent is missing. Yes, transparent is missing, so it works. So when a word in a rational language, a word accepted by the automata will be the following. You start from the initial state, then you read the first letter of the word, read the first letter, then it goes to another state, then read the second letter, apply the transition function, and then so the automata is going to read the word. Each time you're in a certain state, you read the next letter, you go to another state, and at the end, you want that you get in the final state. So all the words you can obtain like this are called the word accepted by the finite automata, and such words belong to the class of what is called a rational language, because if the states are finite states, then there will be rational generating function, and rational language are a special case of algebraic language. All the rewriting rule will be always only one capital letter, always on the left. There will be no several capital letters in the same word, and this is the analogy of a transition matrix. And we have already done this idea of automata in the previous, when we were counting the generating function for Fibonacci polynomial. You remember there is this graph with T. This was the transition matrix and bijection between the matching and such paths. In fact, what we were doing is to have this automata. You start with S1. When there is an isolated point, you read A. When you have a dimer, you read B, B. So the initial state is S1, final state is S1. When I am doing this, means I am reading isolated point. When I am reading the first part of the dimers, means I am going to another state. This means in S2, I started to read the dimers, so I must go back to read the second part of the dimers. So reading this matching, giving the Fibonacci polynomial, is exactly in bijection with reading the word accepted by this automata, and this word are exactly all the words. The language accepted by this automata is all the words which are a sequence of A and word BB. It's a very simple rational language. It's a product. This means union of the two, and this means product of all words A or BB. And in fact, this is a partial automata because when I am in this state, applying the letter A, I don't go to nothing. It will be the same thing. Word accepted by partial automata is the same as word accepted by deterministic automata. You can go, when you apply A, you can go to a hole and then you will be stuck in this. So partial automata gives the same class of language, rational language. And
Partial
so
means not all
partial, yes, there is not all the transition. For example, here there is not the transition A, but it does not matter. You can always add another state where with A you go in the hole and you are stuck here, and the final state will not be the hole, it will be this one. For example, for the exercise, try to show that the vertical convex polynomials are enumerated by this. It's exactly, if you apply the philosophy of automata, you are in a certain state, the first state, S1, and then you go up, you still keep in S1, but you have one time, you have to change the state to say, okay, I will, if you go to another state, I will mark this cell to know that the next time I'm going to stop this, I will go back to this. So try to apply the methodology of automata to find the bijection between this, and reading column by column your polynomial will mean you are moving in a certain finite automata, and each state means some state means, okay, I finish the column, I go to the next one, and the next one I already mark my where I have to put the next one. So I mark this, but maybe you are marking the next one, you go back, and then maybe the next one is also the same. Well, this is try it, and I will give the solution. It's not too complicated, but so I will finish. It's 3 or 10 more minutes. So algebraic, definite now. Now it was rational algebraic with rational algebraic language. Now what about definite power series? So I did not prove this, but you see we have rational algebraic. Before it was given p-recursive power series because there's a polynomial recursion on the coefficient. If the polynomial are constant, it's a rational derivative polynomial. But if there are polynomial in it, this is called polynomial, or definite, because it's equivalent to say that the vector space generated by the power series and all the derivative, the vector space is a finite dimension. And now we call this holonomic also. Sometimes you will see all these terms are the same. There is many power series like this. And a very nice example of definite power series. I have done at the beginning n factorial is a definite power series, but it's very trivial. Now non-trivial power series which are definite. So there is in the last 10 years or 15 years there was many work on paths in a quadrant with elementary step like this. So you just limit the path to be in this quadrant n by n on the square lattice, and you take paths having this kind of step. North, east, west, northwest, all possible steps like this, starting at the origin and maybe going back at the origin. So up to there is some trivial paths which are in fact paths in one dimension. There is some symmetry. So up some transformation symmetry. There is 79 different cases of paths. Among the 79, 23 are definite, 56 are not definite. Now the classification is totally done. It's very beautiful result. And 4 of the definite are in fact algebraic. So why all this? The 4 algebraic are this one. There is a famous Crevera's path. There's a very nice formula for this with bijective proof, which I've linked recently. This is a Gessel path, which I've done a lot of literature because it was very hard. Some people find finally the expression with hypergeometric function. And very late it was recognized that it was algebraic. At the beginning, nobody knows that it was algebraic, and this was very difficult. So there is 4 algebraic family of paths among the defined.
Motzkin path should be there.
Motzkin is in one dimension. No, they eliminate all the trivial case. Motzkin is on the vertical line. So it's a real two-dimensional. And there is this catalytic kernel methodology. This is the way Toth found the formula, the system equation for the planar maps. You have to introduce an extra variable. And with this extra variable, then you have the recursive decomposition of planar maps, but you need an extra variable. That you will, at the end, you eliminate the extra variable. This is called, like in chemistry, a catalytic variable. This was methodology of catalytic, the word introduced by Zalberger. You introduce a new variable, and for example, for the vertically convex polyomino, not necessarily directed, you see, if you want to count such a thing, in particular the exercise of the directed convex, which give you Fibonacci, if you want to count such a thing by area, by perimeter, one possibility is you count the number of such things by the number of cells plus the perimeter, and then if you count also a second variable is the number of cells in the last column. So if you put the number of cells in the last column, then you have some recursive, some functional equation with an extra variable. And then, but you have at the end to eliminate this extra variable. So there is some technique which are outside, so I will not say a word on this, just a flavor, because it's totally outside of the philosophy of bijection. But you need to know this technique not to be completely stupid. It's, if you know only bijection, then you never heard of this methodology of catalytic variable. So all these planar maps, and in general, when you have one catalytic variable, this gives you algebraic generating function. But now if you have two, the path, you can, there is some immediate recursive relation. If you put two extra variables, the coordinate of the last point of the path, then you have a functional equation immediate from the path. Because if you have the last step, okay, if you know which kind of step you have, then you can have recursive relation introducing these two catalytic variables. And then this is the way it was solved. And in fact, there is a kernel method and there is a group associated in this method. And the very nice thing is there is a group associated to the path. And to be definite is exactly equivalent to say that this group is finite. And if it's not definite, the group is infinite. And this is the queen of this methodology. She has spent many papers, Mireille Bousquet-Melou from Bordeaux. All different groups. It's a, no, it's a D2, D6, some simple, some nice group.
What is the biggest group?
No, it's a small group, infinite. In the infinite case, of course, it's big. But look the paper of Mireille Bousquet-Melou. There is one with me. But there is many papers because at the beginning they classify all the paths, but this was a conjecture that not definite means infinite. But this is nice. And to finish, connected heaps of dimer is above the classification. It's not definite, but the generating function has a nice expression. So we handle also in this classification of generating function, rational, algebraic, definite. Some of them are not definite, but you can still get.
What is Q?
Q is a generating function for Catalan. It's Catalan. Okay, I will finish with this beautiful non-definite generating function. And don't try to get a bijective proof of this. There is one. Even you can make bijection at this level of generating function. Okay, thank you very much.